And look, there are guitarists over there.
Wait a minute. Have you ever wondered how a guitar can produce so many different notes?
That's true. The string looks similar, but the voice or the sound are different.
And when the guitarist press the string on different position, the pitch changes.
So, what actually happens to the string that creates different musical notes?
Huh. So let's find out through concept standing wave.
Good morning, everyone. We are Group 5, and today we are going to present our topic, which is standing wave in musical instrument.
Foto kita blue, tak banyak yang kulihat. Foto kita blue, tapi banyak yang aku ingat. Foto kita blue, kita pernah begitu dekat. Foto kita blue.
For our learning objective is to define standing wave, explain how standing wave are formed, and understand standing wave in string and one instrument, and explain how standing wave affect musical pitch.
A standing wave is formed when two waves with the same frequency and amplitude travel in opposite directions and interfere with each other. In a guitar, this happens because the wave created by plucking the string reflects back from both fixed ends. As a result, the string forms a standing waves with notes where there is no movement and empty notes where the vibration is the greatest. This vibration is what allows the guitar to produce a clear musical note.
Okay, let's talk about notes and antinotes in standing wave. A note is a point where there is zero displacement, which means that part of the wave does not move at all. On the other hand, an antinote is a point where the wave has maximum displacement, so it's moved the most. As you can see in the diagram, the blue letter N represents the notes, while the red letter A represents the antinotes. These points are formed because two waves of the same frequency travel in opposite direction and interfere with each other.
Let's look at standing wave in string instrument. Example of string instrument are guitar, violin, and piano. When a string vibrates, the wave reflects from both fixed ends and will interfere to form a standing wave. Different standing wave patterns will produce different musical notes.
Now that we have learned how standing waves are formed, let's observe this concept on a real guitar.
The skyscraper.
First, let's pluck an open string. When the string is plucked, it begins to vibrate.
Causing vertigo. The countdown begins.
As the string vibrates, a wave travels from one end of the string to the other. Since both ends are fixed, the wave reflects back. The incoming and reflected waves continuously overlap, forming a standing wave.
In Tokyo.
Those two ends remain fixed, so they act as notes. The middle of the string vibrates the most, forming an antinote. This vibration produces the musical note that we hear. This demonstrates how standing waves are formed on a vibrating guitar string, allowing the instrument to produce a stable musical note.
Next, let's look at the fundamental frequency, also called the first harmonic. This is the lowest frequency that can produce a standing wave. For the fundamental mode, the wavelength is equals to 2L, where L is the length of the string or tube. The formula of the frequency is F equals to V over 2L, where V is the wave speed. The diagram shows that there are two notes at the ends and one antinote in the middle.
Next, let's look at harmonic. For the first harmonic, also called as the fundamental frequency, will produce the lowest note. For n equal to 1, the wavelength is lambda equal to 2L and the frequency is f equal to v over 2L, where L is the string length and v is the wave speed. As shown in the diagram, the first harmonic has one loop, the second harmonic has two loops, and the third harmonic has three loops. As the harmonic number increase, the string will vibrate in more sections. The wavelength will become shorter and the frequency become higher, with producing higher pitch. For the second harmonic, n equal to 2, the wavelength is lambda equal to L and the frequency is 2F. And lastly, for the third harmonic, n equal to 3, the wavelength is lambda equal to 2L over 3 and the frequency is 3F.
Have you noticed that pressing different frets change the sound of the guitar? This happens because pressing a fret shortens the vibrating length of the string. According to this equation, the frequency is inversely proportional to the string length. So when the string becomes shorter, the frequency increases. A higher frequency will produce a higher pitch. That's why different frets create different musical notes.
Let's see how standing waves are used in wind instruments. Examples of wind instruments are the flute, clarinets, and trumpets. When a musician blows air into this instrument, the air inside vibrates and forms standing waves. Different lengths of the air column produce different frequency. This is why each instrument can play different musical notes.
Now, let's compare open pipe and closed pipe. An open pipe has both ends open, so it produces all harmonic. The wavelength is lambda equal to 2L over n and the frequency is f equal to nv over 2L. A closed pipe has a end closed and one end open, so it produces only odd harmonic. The wavelength is lambda equal to 4L over n and the frequency is f equal to nv over 4L. This is why open pipe and closed pipe produce different sound.
Standing waves are not only important in guitars, but they are also used in many areas of music and engineering. In musical instrument design, standing waves help produce accurate musical notes. In sound engineering, they help engineers to improve sound quality during recording and live performance. They are also important in acoustic system and concert hall design, where a controlling sound reflections creates a better listening experience.
Whoa! So now we know how guitar produce a different notes.
A standing wave forms when the wave reflect and interfere along the string.
Changing the vibrating length will change the frequency and therefore change the pitch.
The same concept also applies to wind instrument
Through vibrating air column.
To conclude, standing waves are formed by the interference of two waves moving in opposite direction. Many musical instruments use standing waves to produce sound. The frequency of the wave determines the pitch of the sound. Lastly, harmonic affect the quality or tone of the sound, making different instruments sound unique even when playing the same note. That's all from our presentation. Thank you for your attention. Bye!
Memilih nama panggilan mesra, kamu blueberry dan aku pastry. Nama depanku, nama belakangku, jadi nama toko roti.
3, 4.
Dengarkan bibirku berbicara, tapi dari hatiku yang kini sepi. Kenapa pula perlu berpisah bila semua punya cinta di jiwa? Apapun ini selamanya, ataupun ini hanya seketika. Kenangan yang tersimpan di hati sampai mati, janji ulang dan kesuai.